Let us go for SNGP. Nothing but neighboring group participation. Also known as anchimeric assistance. We'll tell you what this is, taking an example. Now this actually occurs in two steps. Coming to step one, see here, this L is the leaving group. And see this Z, which has got a pair of electrons, non-bonded. It in fact acts as nucleophile. Okay. Now see what happens. The lone pair attacks this carbon. At the same time, the leaving group goes off. This is a kind of SN2. Which of course results in inverted configuration. Okay. Now this Z will carry a positive charge. Earlier it had 3 electrons, 1 plus 2, 3 electrons, but now it has only 2 electrons. So a positive charge. And the leaving group has gone out with the bonded. Now the step 2. Let us again take this. Now the attack of the nucleophile. As and when it attacks the carbon which actually had the leaving group, then the bonded pair again goes back to the group that had the electron pair earlier. Now this again is a kind of SN2, right? Finally giving rise to a retention product. Look at this. So here you get a retention product. Actually involves two SN2 reactions, both causing inversion, but the net result is retention. So this way, two SN2 reactions finally give a retention product. Okay. So this is the basic neighboring group participation. Here, the neighboring group is the one that has a pair of electrons. Z is what we have considered. So it is actually assisting the carbon from where the leaving group has left. It is, in fact, providing the pair of electron that it has to the carbon from where the leaving group has left. This is why we call it anchimeric assistance. So there are different types of NGP. Look at the different varieties. So this is going to attack. Immediately the leaving group just goes off. Okay. This is the leaving group. Now we get this. Positive charge, carbon, and this. See, in this there is an interesting thing. Look at these two carbons. See, this one is less hindered or less crowded. See, because it has only a hydrogen and a methyl group, whereas this one is more hindered as it has two methyl groups. More hindered. So obviously, the nucleophile finds it easy to attack on something which is less hindered. Means that carbon which is adjacent to the carbon that actually had the leaving group. So that is interesting here. And now that goes to this carbon. So this is something different. The nucleophile attacks a carbon which is adjacent to the carbon that had leaving group. Finally, we get this. Nucleophile, then H. In this case, nucleophile does not attack the carbon from where the leaving group had left, but attacks the carbon to which neighboring group, I mean that Z, was originally connected. So this is something different from what we have seen earlier. Okay. Now let us take one more example where the neighboring group will be a different one. Look at a heteroatom. Say this will now act as the neighboring group. It attacks this carbon from where the leaving group goes off. So Cl minus is last. And look at what we get. This now a bond between this nitrogen and carbon. Now the nitrogen gets a positive charge. And now when a nucleophile attacks, where does it attack? This carbon, so that this bond can be given to the positive charge. Or this carbon, so that this bond can be given. Let us check. You know, this carbon is having only two hydrogens, less hindered or less crowded. Whereas this carbon has a hydrogen, has ethyl group, so is more hindered. So obviously, the OH minus attacks something which is less hindered, finds it easy to attack. Okay, so this is how we get the final product. CH having ethyl group, onto the other hand, the CH2 which has got a OH group. So this is another variety. Now, let us go for this. A different one. Now from here, see what happens. The pair of electron is given. Then this goes off. So minus X minus. Okay. You still have a pair of electron, then a positive charge. Now simply a proton is last and you get a cyclic ether. Now because it is anyway stable, as the intermediate that we got after neighboring group participation is stabilized, there won't be any nucleophilic attack. That's it. The reaction ends here because it is anyway stable. Okay, so this is another variety. Intermediate formed after NGP may sometimes get stabilized So nucleophile does not attack at all. Doesn't even attack. Now, one more. So these are all different neighboring groups. N, O, and now it is S, the sulfur, different heteroatoms. Look at this. So here, the heteroatom is this sulfur. It acts as a neighboring group. Now, as and when this attacks the carbon carrying the halide, the halogen, the halide goes off in, of course, a slow step. Okay. Then we get this particular cyclic one, CH2. You got a CH2 here. These two are connected to sulfur, which is still having a pair of electron. And of course, an alkyl group will get a positive charge here. Now, as and when a nucleophile, in fact, here we are using a solvent as a nucleophile. This can be called salvalysis, just like the SN1. Now look at this. Acts as nucleophile, attacks this carbon. Of course, both are in the same environment. Both the carbons, this and this, are in the same environment. So can attack either of these. In general, attack happens on the less hindered carbon, right? Now look at what happens. Yes. We get this. RS, sulfur will have both its pairs, then this CH2 and the other CH2 to which the water molecule got connected, on which it has attacked. Look at this. Okay. Now, of course, a proton is lost as usual. Take it this way. We get R, S, then CH2, then this CH2, then this OH minus H plus. A proton is lost. Come on. Okay. So this way, we can go for a different neighboring group. These are the different examples for NGP. Let us go for more. Look at this. The lone pair on oxygen. Chloride is lost in a slow step. Then we get O. Yes, it still has a pair of electron, then a hydrogen, a positive charge on oxygen, right? Now, as usual, as seen in the previous case, a proton is lost and we get this cyclic ether called tetrahydrofuran, TH. Now, if suppose we compare the rate of this reaction with something of this type, here I am taking brosylate, just like tosylate, this is brosylate, brosylate, you can say. A very good leaving group again. Now, this attacks, this one goes up. Now, here we will have an interesting point. A positive charge. But you know, this positive charge is more stabilized by the methyl group attached, right? Now, attack of the nucleophile. Let us take acetate ion. Of course, this is a fast step. Now, this will attack the carbon. This will immediately go towards the oxygen. Okay, finally, giving rise to this particular compound, OCH3, oxygen with both its pair of electrons, then this with OAC. Mechanism is same, but see, in this case it is already stabilized, but in this case you got an attack of the nucleophile. Now, one last example, wherein you got a double bond which is acting as an neighboring group. Interesting. So here this double bond is acting as neighboring group. Now look at what happens. As and when the double bond, I mean the pi bond attacks, this goes up. Tosyl minus OTS minus goes off in a slow step. Look at what we get. Now, here you got a bond. This bond has gone off. Okay. I mean, this of course can be given as bond breaking. You are going to form a bond with this carbon, right? So here this will have a positive charge, and even this also will have a positive charge. because from here you actually lost a tosyl group, and here this one is going to lose a bond. Now look at what happens. So this bond is going to get formed. Okay. But you know, as and when the nucleophile attacks, of course, bond formation. But see, as and when the nucleophile, the same nucleophile, what we have taken earlier, attacks on this particular carbon, this goes back. Okay. So finally giving rise to this particular product. CH3, CH3 double bond. You got a CH, then what? You got this bond, then the CH2, which is now connected to OAC. Okay. This is how a double bond also can act as neighboring group. Okay. These are the different types of nucleophilic substitution reactions that we generally come across. Okay. We'll now go for some properties, physical as well as chemical properties. Coming to physical properties of the alkyl halides. You know, the melting and boiling point increase as the molar mass increases. It is because with increase in molar mass, van der Waals forces increase. Okay. Now, supposing if we take the same alkyl group, I mean for the same alkyl group, but halogens are different. You know, boiling point increases with the increase in the molar mass of halogen atom. Okay, we can give it this way. Alkyl iodides, then bromides, then chlorides, and least is for fluorides. Okay. Then we can also say that the boiling point increases with the increase in the number of halogen atoms. And here the condition is when the number of carbon atoms is same. Let me give you an example. 2 halogen atoms, then 3 halogen atoms, then 4 halogen. Now, if suppose we take the same halogen atom, for the same halogen atom, boiling point increases as the size of the alkyl group increases. Okay. Let me give you this example. Methyl chloride, then say ethyl chloride, then propyl chloride. As the size of the alkyl group increases, the boiling point increases. Okay.